Okay, good evening, everyone. Today we'll pick up with lecture 9. I'm going to do it in 2 parts, as I usually do, and we're going to continue with the addition of HX to alkenes. Okay, and let's write the time here. I'll redraw that transformation that we had left off with in the last class. So we had trans 2-butene plus HCl. And the initial reaction, the initial errors that we pushed were from the alkene. We had that pi bond attacking the proton, break the HCl bond, push the electrons onto chlorine. And we said that that generates a carbocation intermediate plus chloride. And then in a second step, the chloride bites back in and attacks the carbocation. And so I can draw a lone pair there to be explicit. And then the product then is this that product there, okay? And so I'm not drawing all the hydrogens. And so we covered that in detail with color in the last lecture, so I point you to that if you want to a more explicit drawing. We then generated a reaction progress energy diagram where we always plot energy on the y-axis and reaction progress on the x-axis. And we put the reactants on the left, so trans 2-butene plus HCl. Those have some finite energy associated with them. We then draw our carbocation. Plus chloride, okay? And then we can draw the products. And so the product, and that will be down here. And then we can connect these with lines. And so we'll draw a line with the saddle up to the carbocation, and then a second line with the lower saddle down to the products, okay? The tops of these saddles are what we refer to as the transition states. And so this is TS1 and this is TS2, okay? And the transition states are those points in the reaction pathway where you're making and breaking bonds, okay? So it's sort of like what happens between starting materials and intermediates, okay? And so we're going to add a lot of detail to these charts. And the first idea that we want to introduce is what's known as the activation energy. And okay, and we use a double dagger to indicate that we're referring to a transition state. Okay, and so the activation energy is the energy from the reactants to the highest energy transition state. And so The energies of TS1 and TS2 in this reaction are not equal. TS2 is in fact lower in energy. That is not always the case. Sometimes TS2 is higher. We'll explain this more in a second. But the difference in energy to that highest energy transition state from the reactants to the highest energy transition state is what we're going to be most concerned with. And so we call that delta G double dagger. Okay. We refer to the carbocation and chloride as intermediates. So intermediates are bona fide compounds en route to a product. And so they undergo further transformation, but they themselves are discrete intermediates, discrete entities along the pathway. The transition states are what happens between the bond forming and bond breaking sort of orientations of the molecules between reactants and intermediates, or intermediates and products, okay? And so there's a couple things that we want to introduce here. And the first thing that we want to introduce is what's known as the rate constant, which is typically designated lowercase k. Okay, and this refers to how fast, it's a property of every reaction, and it refers to how fast the reaction occurs. And so it has a specific definition, which is kappa T over H e to the minus delta G double dagger over RT, where kappa is Boltzmann's constant. Oops. Shoot. This thing, the picture just got in my way here. Okay. Kappa is Boltzmann's constant. The H is Planck's constant. T is temperature in Kelvin. R is the universal gas constant. Okay, and we just defined delta G, double dagger, okay? We can simplify this equation by lumping kappa, T, and H all together. And so we can just say K is proportional to E to the minus delta G double dagger over RT, okay? Because we just want to understand the shape of this function. And so if you plot any sort of function, you know, e to the minus x looks something like this, right? And so what does this tell us? Let me rewrite it on this slide. So okay. What this tells us is that as that delta G is going to get larger, right? The rate is going to decrease, right? So as the rate increases, K is going to decrease. Alternatively, if you increase the temperature, you decrease the size of that quotient, right? And so as T increases, so does K. Okay. And so again, we don't, concern ourselves too much with, with the actual values of K, at least in this class. If you ever take a kinetics class, this is bread and butter. We're just concerned about the trends. And so high activation energy, high value of delta G double dagger corresponds to a slow reaction rate, slow reaction, slow progression of starting materials to products. As that activation energy goes down, it becomes much easier for starting material to go to product and the rate of reaction increases. As the temperature increases, the rate also increases, and you can think about that intuitively. You're giving more energy to the molecules. They have enough energy to get over that barrier, okay? And so what I want to spend a little bit of time talking about are the very important carbocation intermediates. And these are critical intermediates because they're going to come up in a lot of reactions, and there's important sort of concepts, this concept of hyperconjugation that we'll introduce that is very sort of general in organic chemistry. So I redraw our cation here. Okay. And so if I want to draw this more explicitly, I can put the hydrogens in. Okay, and my positive charge on carbon. And so then we want to think about the geometry of this carbon. And so it has three things attached. And so according to the Vesper model, it's going to be trigonal, planar. The bond angles between the substituents are going to be close to 120 degrees. And so if I draw this with perspective, it looks something like this. Okay. And the question then is, what's the hybridization at carbon? Okay, and so I've got 3 ligands. I want to use identical orbitals to make the bonds to those ligands. So I need 3 identical orbitals. So I take my 2s, combine it with 2 of my 2p orbitals, and I get 3 sp2 orbitals. And those form the bonds to the substituents on carbon. So okay, so the carbon is sp2 hybridized, and the sigma bonds are formed with csp2 orbitals. And so what's left, I still have 1 more orbital unaccounted for. That's my 2p orbital, okay? And that is perpendicular to the plane defined by the carbon and its substituents. And that orbital is empty. Because I have a positive charge at carbon, okay? And so that is the geometry of a carbocation. So sp2 hybridized, planar, with an empty 2p orbital perpendicular to the plane defined by the atoms. There's an important stability trend in terms of carbocations. So carbocations are high energy intermediates. I've only got 6 electrons around carbon. It's very unhappy. It really wants to pick up 2 more electrons to fill its octet, okay? And so these things, because they're high energy intermediates, are very sensitive to their environment, okay? And it turns out that as I start to introduce more carbon atoms directly adjacent to the carbocation, the stability of the carbocation increases. And so let me give you 3 examples. So okay, so we can think about, put the butene aside for a second. This type of carbocation where it got 1 carbon attached, you can think about a carbocation where it got 2 attached, 2 carbons attached, and 1 even where it got 3 attached. Okay. You know, these are so common. The substitution pattern is so important. We give these special names. So this is called a primary cation. This is a secondary, and this is a tertiary. Okay. The energies of these things are well known. The tertiary is the most stable. And so if we call that 0, we can then write out the relative energies. So the secondary cation is uphill by about 16 kcals per mole, and the primary is about 35 kcals per mole. So okay, so primary, least stable carbocation, tertiary, most stable, secondary in the middle. Okay, and so the question is, this is Black Cat. Come here, sweetie. All right. The question is, where does that stability come from? And this is where hyperconjugation comes into play. So I'm going to give it to you in sort of an orbital diagram. And so if we consider just the ethyl cation, CH3, CH2+, and I draw this out with perspective, you've got 2 hydrogens on that terminal carbon that has the positive charge. And then I've got a methyl group to the left, okay? And what I'm going to intentionally do here is draw one of those CH bonds in plane with the whiteboard. So like this, okay? And then the other 2 are going to be like this. And so what hyperconjugation is the donation of electron density from an adjacent CH bond into an empty 2p orbital. So if we consider just the sigma bond, okay, that sigma bond, which bears 2 electrons, can share its electron density with the empty 2p orbital, okay? And so this may seem very strange, and that's okay. It should. You haven't seen this before, all right? What we're basically doing is using a sigma bond as an electron donor, okay? The reason this works is because it's right next to the cation, it's almost parallel, and it has the correct symmetry. So you can get all of the signs to be sort of consistent. Okay, and so the way we can represent that electron density is just by using arrows to sort of generically show the electrons being distributed to the 2p orbitals. So let me write it out explicitly. So okay, and so this is a stabilizing effect. All right. We can also, so that's sort of a schematic. We can also put this into an MO diagram. And again, you haven't seen this explicitly, but the principles of what we've done before in terms of constructing MOs from AOs are, it follows parallel set of rules, okay? And so, you know, it's sort of a truism of quantum mechanics that any orbitals of the can interact provided they're of the same symmetry, okay? And if you look just qualitatively at this diagram, I've got a big lobe between the C and the H that I can make the same sign as the 2p, and then the little lobe sticking down has a flip sign, and so does the 2p. So they have the same symmetry, and so the math tells us that they can interact. Even though this may seem strange, it's following the same principles as the AOs. And so I can generate a diagram in the same way. Okay, and I'm going to put the sigma CH bonding orbital lower in energy than the C2p. It's a bonding orbital. The electrons are stable. It has 2 electrons. And then you can allow those to interact, and you get a bonding and non-bonding or anti-bonding interaction. Okay. And the 2 electrons go into the bonding orbital. Okay. And so this is just another perspective on the drawing, you know, another take on what I'm showing you in that drawing on top. All right. We don't need to concern ourselves with the shapes of the resulting orbitals. You know, they look a little bit like pi bonds, you might imagine. The point is that when I allow them to mix, what am I doing with the electrons in the CH bond? They're going down in energy, okay? And so anytime I can move orbitals to what is electrons to an effectively more stable orbital, that is stabilizing. So okay. And so let me just say it one more time. So hyperconjugation is the overlap of a sigma CH bond with an empty 2p orbital, okay? The MO diagram is on the bottom here, and we can draw all sorts of perturbations for this to describe tons of other types of interactions. So we can draw nitrogen lone pairs interacting with C2p, or oxygen lone pairs, or carbon-carbon sigma bonds. It's all the same type of interaction. The magnitude of that interaction varies, and understanding those qualitatively is important, but the principles are exactly the same, okay? And maybe another way to think about this is to think about that sigma CH bond as kind of like a funny looking 2p orbital, right? Like it has same symmetry as a 2p orbital. If I put 2 C2p orbitals adjacent to each other, you'd say that made a pi bond. It's the same type of interaction here. except the shape of the CH bond is different. And of course, the electrons, both electrons are coming from one orbital as opposed to two half-filled atomic orbitals, okay? And so the important point is that protonation, the first step in the addition, always occurs to generate the more stable carbocation. So okay, and so if you think about, for example, 1-butene as opposed to 2-butene, there are two different ways that I could protonate this alkene. I can protonate at the terminal carbon or at the internal one. And if I protonate at the terminal carbon, so I'll just make my HCl green so you can see where the protons end up. Okay, so if I protonate at the terminal carbon, I get that carbocation on the left. That is a secondary carbocation, okay? And if I protonate at the internal carbon, I get the carbocation on the right, and that is a primary carbocation, okay? And so we are always going to favor the more stable carbocation, all right? And so we will always protonate for 1-butene in a way that I generate the secondary carbocation. And so what this means then is that chloride traps this to form the more substituted product. Okay, and by more substituted, I mean the chloride is bonded to the carbon that bears more carbons, okay? The alternative reaction pathway where chloride traps to form the linear product or the less substituted product is not observed, so. Okay, that one is not formed. And the reason it's not formed is because of the stability of the carbocation preceding it. And so we always want to form that more substituted, more stable carbocation, all right? And so I can put this on an energy diagram to show you the differences. And so I will go to another slide, but I'm going to stop the video and then we'll pick up in a second here.